So, hey guys, today we'll be looking at a grade 11 math problem. It deals with coming up with a function and optimization and the domain and range. So let's get started. It says a farmer has 450 meters of fencing to enclose a rectangular area, which is this. And then divide that into two sections. So, like that. And then for part A, we're asked to find the equation to express the total area as a function of the width. For part B, we have to find the domain and range of the area function that we made in part A. And then for part C, we have to find the dimensions that will give us the maximum area. Okay, so yeah, let's get started. Okay, so basically, we're given 450 meters of fencing. So what that means is that it's gonna, the fence is gonna cover not only the entire perimeter of the rectangular enclosure, but also this part as well. So, if you just look at a rectangle in general, we know that it consists of length and width. So, in this case, if you consider this side to be L, then this side is also L. And if this is the width, then this is also the width, and so is this. So we're dealing with 2 lengths and then 3 widths. And so I've defined that here as well. W for width and L for length. And so first, we have to come up with a general equation that deals with the perimeter of the rectangle. And this piece as well. So, as I mentioned just now, we have 2 lengths and 3 widths. So the sum of the 2 lengths plus 3 widths, it has to be equal to 450 because 450 is the given amount of fencing. So next, if we were to isolate L, we come up with this equation. So we let basically W, we denote W for width, and for length, which is L, we have this equation. For step 2, we know that the area of a rectangle is length times width. So basically, length, which we got from here, times the width. And so that means our area function, or area of the function of the width, is basically what we wrote here. So that's our answer for part A. Area as a function of width is this. Okay, so for part B, it asks us to find the domain and range of the area function, so which is this one. Alright, so this is a bit more, I guess you could say, complicated. It's not too hard, so let's just get started on this one. So basically, what I did for part B is that, so the area function that we got in part A, I expanded it, so I multiplied W by this bracket here, by the length, and which gave me this new equation. Let me just highlight that in green. It's the same equation, but it's just expanded now. Okay, so basically expanded this and I got this. Okay, and so we know for a quadratic equation, the general form is y equals to ax squared plus bx plus c. Okay, and so for this equation, the negative 1.5 is our a value, and 225 is b, and c is 0. Okay, and just take a general rule, as you can see here. So a is equal to negative 1.5. Actually, let me just write that down on the side. Okay, so these are the 3 values for a, b, and c. And so because a is a negative, we know that in general, the parabola, so this is the x-axis and this is the y-axis. Oops, sorry. So this is the x-axis and this is the y-axis. We know that because the value of a is negative 1.5, or because it has that negative, the parabola is going to be pointing down. I guess you could just say the general rule would be if a is positive, then you would have a smiley face, and if a is negative, then you would have a sad face. So I guess that's like the general rule for a parabola. And okay, so basically we have a parabola pointing downwards, and so that means it will have a maximum, right? And so that maximum can be denoted by h and k. Okay, and next step would be to find the x-intercept of that of this equation. Okay, so what we do is you take the function, set it equals to 0, and you solve for it. So one value would be w is equal to 0, and the other is 150. Okay, and next we have to find the values of h and k. Okay, so basically the general, I guess, formula you could say to find h and k, this, and I believe this also applies to find the minimum point as well, but I'm not too sure about that. So for maximum point, this is the formula that you have to use. But yeah, I'm pretty sure it's the same formula for a minimum point as well. So we know that the values for A and B and C, which we have determined, so we just plug them into this formula. So for H, which is minus B over 2A, we plug in the values, and we got the value for H, which is 75. Now, to find the value of K, we take this value for H, which was 75, we plug it into this function, which is this one, and we get the value as being 8,437.5. Okay, so let me just zoom out. So I just made a general, like a small parabola here, and so basically we determined the two x-intercepts, which were 0 and 150, so I put those here, 0 and then 150, and then the maximum point is 75 and 8,437.5. So I just made like a small graph for you guys to better understand this. And so basically the parabola is pointing down because the value of A was negative, so it makes basically like a sad face. So as a maximum point, which we've determined, and then the two x-intercepts. Okay, so then now from here it'll be easy for us to find the domain and range. Okay, so for the domain and range, we've determined from the graph that, or from these previous steps, that the two x-intercepts are the domain. Alright, so it's 0 and 150. And because this is a real life problem, we should understand that the lowest value for the width, or in any like general real problem, is always going to be 0. So just keep in mind. And so we've determined that 0 and 150 were our two x-intercepts, and so you know that the whole the graph, I guess, will go from 0 and will end all the way at 150. So that's our domain. the width belongs to all real numbers, where the condition is that width lies between 0 and 150. Alright, and the reason why it's not less than and equal to, or sorry, greater than equal to and less than equal to, is because from this graph we can see that if we plug in, or even if you don't plug in, we can just see that when the value of the width is 0, AW, or the area, is 0, and then at 150, or when the width is 150, the area is also 0. So that can't be possible. You can't really have something that has an area of 0. So that's why here we have to, it's greater than and then less than, not less than or equal to or greater than or equal to. And so similarly for the range, it says the area belongs to all real numbers, where the condition is that the area, again, it's greater than 0 because it's a real life problem. Anything that has an area will always be greater than 0. And from the graph, we know that the maximum point for the area is 8,437.5. So that basically is our range. So area lies between 0 and then 8,437.5. Okay, and so yeah, just keep that in mind, that for like these type of real life problems or real life applications, any length, like length or width or area or perimeter, can never be equal to 0. So that's why we did not include the equal sign here and here. But for this case, because the area is the maximum at 8,437.5, we have to include the equal sign for here. Okay, so that's the domain and range. So that was the answer for part B. And for part C, it says that we have to find the dimensions that give the maximum area. So we've already determined that. We can see that by making a graph, it becomes much more easier to solve the problem. And so it says it's asking for the dimensions that give the maximum area. So from the graph, we can see that the parabola hits its maximum point at 8,437.5. So that's the maximum area, 8,437.5 meters squared, and this area occurs when the width is 75 meters. So yeah, and so that's it. Yeah, thanks for watching. Hope you guys have a nice day. Thank you.